And I'm CAE engineer, working in Midas IT company as the technical support engineer. So today we will spend some time on the basics of Midas NFX software and basics of FEA analysis, but mostly I will be focused on the practical examples to show you the procedure and workflow in linear static analysis. So today there is with me Mr. Apul Sharma and Mr. Sarpian Rusu, and my colleagues will answer your questions during this webinar, so you can ask us using the chat section. Okay, so let's start. So I would like to briefly remind you some basics about midasNFX. We've already provided few webinars related to the basics. So today only few of the slides just to remind what the midasNFX is and just to remind the basic workflow. So midasNFX represents a fully integrated engineering solution package for virtual simulations, and this package is using finite element method. So this application is widely used for all mechanical purposes with additional CFD analysis capability as well. And the software is available as 32 and 64-bit application, and it's working in all Windows platforms from XP, Windows 7, Vista, and Windows 8. So midasNFX has been equipped with very friendly graphical user interface, which is widely known from other engineering solutions as well. At the top of the interface, we see the ribbon bar where all tools and comments has been grouped. To the left, we see the panel, which consists of 3 sheets. So these 3 sheets, thanks to these 3 sheets, we have an access to model all entities like material parameters, loads, and boundary conditions, and we can display the results as well. At the center there is a work plane, and at the bottom there is a message and output window. midasNFX is working in 2 modes, in the designer mode and in the analyst mode. And to the left we see simple screenshot from the designer mode. So, and this mode activates simplified environment, and it's oriented for the beginners or let's say early stage users. So using this mode we can perform simulation quickly, and due to that we can receive the basic information about our model behavior response. The second mode is analyst mode, which is dedicated for advanced users or let's say more experienced user. And in this mode we have full control capability on our modeling process. So we can work directly with the mesh elements, we can work directly with the mesh, and in this mode we have an access to full capabilities of midasNFX. So using these 2 modes, the user can perform all kinds of simulations like linear static, nonlinear static, heat transfer, linear and nonlinear dynamic, and others. So now let's take a look on the geometry and data exchange. So in both modes, midasNFX supports following geometry extensions like STEP, IGES, Parasolid, CATIA version 5, version 4, SolidWorks, ProEngineer, AutoCAD, and STL. Last time we added the Solid Edge extension, and all of these extension versions for the geometrical files has been updated to the latest versions. In terms of CAE, we can import and export our FEA model using the Nastran format, which is widely read by FIMAP, ANSYS, Abacus, and the rest of the most popular pre and post processors. So as I mentioned before, midasNFX is a total solution package, or let's say total integrated package. And this term means first that software includes full pre-processing capability to create your FEA model. So in terms of the geometry related tool, has been grouped inside the geometry ribbon bar. And from this place, we are able to use geometry creation tools like Boolean operations, transformation tools. We can edit our geometry. And also, if we look on the model sheet inside the model workstream panel, we will find the geometry branch, and under this, all geometry entities like points, curves, surfaces, solids, under this branch, all of them will be grouped. Additionally, when the geometry is imported, every part of the assembly will be also colored in the different color. Okay, so in the analysis mode, we have an access to many geometry tools. So basically, we can create all types of the geometry, starting from the point and ending on solid. And I will show you some practical examples during the tutorial session. And to create the geometry, we can use, for example, polylines, arcs, curves. After that, we can transform these entities to 2D and 3D objects. So another step is the extrusion, revolving, sweeping, or perhaps lofting the geometry. We can use primitive shapes like boxes, cylinders, spheres, and this geometry can be also measured because midasNFX provides also measurement and transformation tools. On the next slide, we see few examples of the geometry features. So using this Boolean operation, we can fuse the geometry, for example, cut and empt. Trimming and sewing is supported as well. But one thing we have to remember, and I am repeating this all the time, that this is not CAD tool. So from the practical point of view, it will be more effective to use other CAD application. But in terms of modification, this will be very useful to have these capabilities. On the next slide, we see the element library which has been provided to midasNFX. So let me introduce some basic elements. So to create a FEA model, we can use all of the most popular elements, and there are available solid elements like tetrahedrons, pentahedrons, hexahedrons, pyramids, which are used mostly to measure the solid parts or the solid assemblies. We can use 2D elements like shells, plane stress, plane strain, axisymmetrical elements, composite shells, and typical examples are pressure vessels, sheet metal brackets, some kind of roofs, for example, composite wings. 1D elements like beams, rod, and pipes to model the structures like trusses, frames, bridges, and scalar elements like springs, masses, dampers, fasteners, and also MPC elements, which is called also a ring interpolation link to create some kinematical relationships. Solid meshing, or let's say 3D meshing, will be performed using very effective automated mesh generators. And because midasNFX is working as 64-bit application, due to this fact, the time needed for this discretization process will be less consuming. So application is using all of available processor trees, and this will be resulted in 50% of the time reduction. Let's say if we use even all of these trees. More of that, meshing algorithm will perform some dancing locally in the areas of sudden geometry changing, like notches, holes, etc. And for today, midasNFX is using the following automated algorithm, like Delaunay loop mesh and grid mesh for the 2D meshing, and for the 3D meshing there is a high-speed tetra mesher and hybrid mesher. So I would like to say a few words about this hybrid mesher. So hybrid mesher is using all of solid element types like tetras, hetras, pentas, and pyramid element, which is called also transitional element. And this type of element assures, let's say, continued transition between hexa and tetra. So you can take a look on to the right. So at the center there is a pyramid, and this assures this fluent connection between the rest of the elements. And using this type of measure type, we can widely contribute to minimalization of the FEA model size. And let's take a look on the example to the left. So if we use tetrahedral mesh, only the size of our model is close to 160,000 nodes. But if we use the hybrid measure, we see that the size has been reduced almost 3 times. So this this will be very useful in terms of the reduction of the analysis time. Okay, so similar to the geometry tools, we have an access to advanced mesh modeling tools, and now I'm talking about the manual meshing creation process. And we can create all types of elements starting from node and ending on the solid element. Using this group of tools, we can control the size of the mesh using several control methods like, for example, length, division ratio, and symmetrical distribution for the mesh seeding. We can check the property of the mesh. We can create mesh sets. Some kind of groups can be created. We can group the nodes into tables, connect, disconnect nodes, and similar to the geometry, we can also protrude, revolve, and sweep the mesh from 1D or 2D and create 3D objects. So few examples about working with the mesh tools are shown on the next slide. To the left we see some, for example, some car boot which has been made through the revolve command. Some examples of the extrusion, projection. We can offset elements, fill elements between the mesh surfaces and sweep elements. So all mentioned tools are widely used for high quality mesh generation, and on this slide we see also some examples which has been made using half automatic technique. So we can let's say split our model into few parts, and some parts can be meshed automatically, some parts of our model can be meshed using the manual methods or techniques. So this kind of high quality mesh, as you see on the slide, will assure high quality of the results without any doubts about internal discontinuities or, let's say, bad quality elements, which is very important for FEA analysis. Okay, so material data is very important to provide the stiffness into your model. So for the linear static purposes, we have to provide elastic modulus, for example, and Poisson's ratio, and we can provide this data manually, or we can use the data table, which is also implemented into midasNFX. For today, we have a database which consists of 1,000 materials, and more of that we can specify some default materials. So if you, let's say, working frequently with the steel or many variations of metals, you can directly provide this data into the options, and this information will be stored and it will be loaded every time when you start the work with the software. Right now there's time to say a few words about the boundary conditions and loading. So this is another important step, as you remember from the previous webinars. So if we talking about the boundary conditions, they can be applied on the geometrical objects like points, curves, surfaces, and faces from solids, and on the mesh entities like nodes and faces of the elements as well. This is very important information because, as I said before, in the analyst mode you can work with the mesh on using the geometry or directly with the mesh. So that's why I'm talking about it. So the user has got several options to apply required constraint or support, let's say. So we can use default constraint definitions like fixed, pinned, or symmetrical definitions if we just click on this advanced tab. And we can check the degrees of freedom depending on our needs. So constraints can be specified based on selected reference coordinate system or reference object as well. So let's take a look on the sketch to the left, to the right. So now we see some example of symmetrical constraints, and I will show you exactly the same example during the tutorial session. Now let's take a look on the types of static loads. So similar to boundary conditions, loads can be applied directly to geometry or mesh, which means nodes and elements. So we can apply many types of loads like forces, moments, pressures, translational and rotational displacement, centrifugal forces, follower forces, etc. And all of available types of loads have been grouped in the ribbon bar. An interesting thing is that midasNFX is MSc Excel compatible. So due to this, it's available to import loading from external software or let's say measurement devices and interpolate the loading on your mesh. On the next slide, we see the analysis case setting introduction. So this is the step just before the solution phase. So at the top we see the ribbon bar, and there is an icon or button, let's say, where we can define the analysis case. So after that, when we click on this general, for example, if we use the tree, we can specify the type of analysis, and if it's needed, we can choose needed output vectors, because if we click on this icon, output control, we have an access to choose then the results, like node results or, for example, element results. So this is also very important when we want to reduce the calculation time. So we can request only, let's say, displacement for the calculation. And now let's take a look on the last part for FEA workflow, which is post-processing. And I'm talking about this because the whole pre-processing and solving process takes the most of time of the simulation. So after spending this time on waiting for the solution, it's always good to have right and efficient tools to display achieved results, understand them, and prepare documentation very easily. And similar to the rest of the tools in NFX, post-processing functionality has been grouped inside the results ribbon sheet, and we have a lot of options to display our model using many color schemes. There are some tools for advanced post-processing like probing, graphing, result combination, and others. All of output vectors you will find inside the results works tree, and you have full control on the number and type of the requested output data. And some of the examples for the contour types have been presented on the next slide. So we can display results using full contours, contours with lines, without colors, with the deformed shape, with mesh, without mesh, and, for example, transparent if it's needed. So there are many variations for the post-processing and contour mapping. In NFX, it's also possible to display your results using the Probe tool to get information about your result directly from the node or element. And a very interesting post-processing feature is displaying the graph directly on analyzed parts. So this is this result distribution. And all of the results data are also compatible with Microsoft Excel. So after calculation, you can generate the analysis report directly in the Excel, or this report can be created automatically by NFX. And some, let's say, very sophisticated post-processing tools like clipping plane, isosurface vector plot has been presented on the next slide. And these type of tools allow the user to view the results, let's say, in a graphical manner effectively. So these capabilities are also supported. And that's all about this simple introduction to the linear static analysis and midasNFX software. Now I'm switching to the software directly, and we will perform some examples. And we will start from the simple example which refers to the modeling 1D structures. And you can find this tutorial on the YouTube as well, and in your, let's say, midasNFX training folder. Okay, let's start doing these examples. I would like to say as well that whole this practical session will be provided in, let's say, 3 sections. Right now I'm starting to provide you tutorial about the 1D elements. After that we will analyze 2D example, and after that I will show you some practical example using the analyst mode to create the geometry, and we will perform 3D analysis. So at this moment, let's start create some plane frame model. And as you see, analysis setting dialog box has been displayed. So from the model type, I'm clicking on the 2D, and as the unit system I will use Newton. For the force and for the length I will change the millimeters to meters. So I'm clicking on OK, and let's start sketching the geometry. So right now I'm starting from the geometry, and we are using the midasNFX analyst mode. Okay, so let's click on the polyline, for example, and right now it's necessary to provide the coordinates, so I'm clicking on 0, 0.0. I'm clicking on apply, and I will create vertical lines, so the next coordinates, next relative values will be like following, so 0, 3. I'm clicking on apply and cancel because I want to close this polyline. Okay, so let's hide the grid at this moment and datum axis, and you're supposed to see that the vertical line has been sketched. And at this moment I'm going to use translate command, and I will make a copy of this line. So I'm clicking this object. Let's select the vector for the direction, so I will use the x-axis as the reference. I would like to copy this line, and this time I'm selecting the non-uniform copy option. So I'm clicking, I'm specifying the distance, so this will be 5, for example, and minus 10. I can use the preview button to check. So at this moment you're supposed to see preview of my result. Let's click on OK. So 3 vertical, let's say, lines has been created, and right now I'm creating the horizontal ones. Cancel. Let's close the polyline, and geometry for the plane frame has been created in this moment. The next step is to create the mesh. I can do that because we have a possibility to create, let's say, plot mesh in midasNFX. So I'm clicking on this mesh tab, and from the generate I'm clicking on 1D. Let's set up the division to 1, and we have to provide the orientation for the y-axis. So I will use direct input this time, and this will be refer to the global x-axis. This orientation axis is necessary to orient your one-dimensional models, and when I create the property and section, I will display the local coordinate system, and I will be back to this option. So at this moment, please remember this fact that we are setting up this element y-axis, and our global orientation is parallel to global y, to global x, excuse me. So I'm clicking on OK, and let's select these 3 columns. A property, at this moment I will create the plot mesh, so property is not necessary. Let's change the name to column and keep the value 1. So I can click on the preview, so we see 2 nodes, which means that 1 element will be created. Let's click on apply, and let's do the same with the horizontal edges. So I'm selecting these 2 edges. This time please divide these edges for 4 parts, and this time I have to repeat the same operation related to the orientation. So I'm clicking on this orientation dialog box, and at this moment I'm checking the reference node. So I'm changing the method. You can provide this orientation using direct input or reference node. So this time I'm changing this. So please provide me the node for the reference. So now I'm clicking at this bottom center node, and I'm clicking on OK. We have to change the property because the cross section will be different for the horizontal beams, and let's change the name as beam. I'm clicking on preview, so we see some red dots, and let's click on OK. So at this moment the mesh has been created, and right now I'm clicking on the material branch, and as you see, material has been already created. I mentioned about that during the presentation, so we can set up this material in the options. That's why we have this material. So now I'm clicking on this alloy steel, and let's take a view on the structural parameters. So everything what we need, what we have to provide for the linear static analysis is the elastic modulus and Poisson's ratio. So I have this data because I'm using the data from the database. So at this moment actually everything has been provided. So I'm clicking on OK. And what we have to define is the property, which at this moment this property are under undefined branch. So let's define the property, which means let's provide information about the cross section and shape for our one-dimensional elements. So now I'm right clicking on the first one. So let's define the first property. From this dialog box, let's choose the bar type for the one-dimensional property. So as you see, we have the material, and we have to provide all of this data like cross-sectional area, moments of inertia, and other constants. But if we don't have this data, we can use the cross-section calculator or template. So now I'm clicking on this button, and from the list I'm selecting the required section. So let's specify the dimensions. So the reference for the dimensions has been shown on this picture. So for the dimension number 1, let's enter the value 0.3, and for dimension 0.3, dimension number 4, let's provide 0.01 meter, 0.015, and the same 0.015. So I just created my section. So let's click on OK, and as you see, all of this data has been filled automatically. So now I'm clicking on OK, and let's change the name for the property. At this time, let's change the name for the column, and let's click on OK. So if we go to this property under 1D elements, we can display the section. So now, as you see, I have a property for my 1D mesh. So I can display the section and hide the section as well. So at this moment, let's assign the property for the horizontal beams. So the same procedure, let's define. Let's check the bar. Let's change the name to beams, and let's provide the data using the section template. So I'm clicking on I section, and let's provide this data: 0.45, 0.2, 0.2, 0.09, for example, 0.14, and the last dimension the same, 0.14. So this horizontal beams has got dimensions like following. So I'm clicking on OK, beams, and let's click on OK, and now we can display the plane frame. So our model is almost ready at this moment. Okay, let's hide these cross sections, and now I'm going to the static and heat analysis tab to apply the constraints and loads. So this is the stage for load and boundary condition application. So now I'm clicking on the constraint. From this constraint dialog box, I have to select 3 bottom nodes, and let's use the predefined condition, which is called fixed. And let's click on OK. And additionally, if we go to Advanced tab, we can add additional constraint which will block the movement of the frame along the zeta direction, because we want to keep this frame in the plane. That's why I'm selecting all of the nodes, and I'm clicking on OK. Okay, so this beam has been constrained at this moment, and as I mentioned before, you're supposed to remember that we provided some orientation for the beam. So right now I will display the local coordinate system. So if you remember, I used direct input value to orient this local coordinate system for the beam along the global x-axis. So what we see, the local y-axis is parallel to x global axis. This is very important thing, because x local axis of your element is always aligned with the line, parallel to line. And the same example for the horizontal, our reference node was the middle one. Okay, let's hide this local coordinate system, and at this moment I'm going to assign apply the beam load. So from this dialog box, let's select the edge. So on this edge I will apply some kind of let's say variational distributed force. So my force load type is force, load distribution will be distributed, direction is parallel to the global y, and as you see from the list we have many options to define the direction, and I'm choosing the global y. And we have to provide the values, so I'm using the fraction. So this is the let's say start of the line, this is the end, that's why I will enter the 0, and as the next value will be 1, and this is the fraction. So this define there is no unit, as you see. Fraction means, let's say, unitless values, so 0 and 1. And at the end number a, let's enter the value -1 and -2 for the second end of the line. And using this preview button, you can see that I just created distributed force. This arrow is much shorter than this one, and the force will be distributed along this edge. Okay, so let's approve that. Okay, and let's add some other forces. This time I will use the concentrated force. Let's select this middle node, and the value will be -10,000 newtons. Let's click on the preview, apply, and let's add additional force, for example 5,000 along the x direction for that node. And let's click OK. So at this moment, model has been constrained and loaded and subjected to the load. Okay, so all of these steps, as you remember, material definition, loads and boundary conditions, property, has been done. And right now I'm clicking on the analysis and results, and we have to prepare the analysis conditions. So from this menu I'm selecting the other, and from this dialog box you can specify your case settings. So now let's enter the title. So we see 3 sections in this dialog box. First section includes all of the sets and all information data related to the mesh, boundary conditions, static load, and contacts. This part refers to the active part set, so you can drag and drop the active mesh groups. Actually, you can drag and drop the mesh groups to make them active or inactive. And under this subcase setting, you can define the actual configuration for the boundary conditions and actual acting forces or other loadings. From this output control box, as I presented on during the presentation, we have an access to choose which kind of output vector will be calculated. So I want to get information about the displacement, I want to calculate the stresses and the rest of the output vector. So I'm clicking on OK, and I'm clicking on OK. So let's calculate this. So to start the calculations, I can use this option, which is I'm right clicking on the analysis case, and I can click on the solve button, but I can go as well to the analysis tab and click this button which is called perform. And if we have much more, let's say, analysis cases, we can use them as well. So let's click on OK. Let's save the model. And this model is very, very small, so the analysis time is very, very short, as you see. So the analysis took 0.1 second, and as default, all analysis results will be loaded to the panel to the left. So right now I'm double clicking on the total translation. So now we see the, let's say, contour for the deflection, but to see this in the more effective way, let's say, I will display the cross sections for our beams. So we can display this contour map, we can display the deformation like that, and if this needed, we can also play the animation for our results. So this is some example of the post-processing for 1D. Some additional results related to one-dimensional elements are bending, for example, bending moments. So we can display them. So there is no moment around y-axis, but there are moments around zeta axis. That's why we see some diagrams, and let's hide this information, and we can display the animations with the diagrams as well. What about the other results? If we click on this linear static branch, we can click on this insert analysis results, and from this list we can choose all of calculated output vectors. So now I will click on the select all, and as you see, the list has been updated. So at this moment I can display information about the, for example, translation along the x-axis, some information about the reactions, axial forces, and stresses. Okay, it was all about the one-dimensional example, about working with 1D elements. At this moment, we will make some example with 2D plate. And let's start. So unit system is Newton, millimeter, and similar to previous, we can use 2D environment. So now I'm clicking OK, and we will create the geometrically from the beginning. Okay, so at this moment let's click on the rectangle. Location is 0, 0, so let's apply, and let's define the opposite corner, and the value for the opposite corner values are 10, 30, and let's click on OK. There is a shortcut which is Ctrl Q to magnify the screen, and I will hide the grid and datum axis. Let's create the circle, so the location will be 0, 0 for the work plane, so I'm clicking OK, and radius will be 5. And right now I'm going to the intersect option, and I want to cut these edges. So I have to select all of these edges. In this case, let's click on OK, and as you see, all of the edges has been intersected. So now I'm selecting the unnecessary edges. I'm pressing delete and OK. And if I hide this work plane, you can see that I could prepare let's say quarter of the plate with the hole, and this is the topic for this exercise. So at this moment I'm clicking on the make wire option, and I can create the face or region if I want. So it's in this case actually let's create the region. So this, let's say, geometrical object will be not face, but according to this region definition, it will be treated almost like a face for the meshing. So okay, let's click on that. So now instead of many edges, I have one continuous wire. Okay, so the geometry has been prepared, and right now I'm clicking on the mesh, generate 2D, and let's select the auto area. So let's select all of these edges. Once again, let's specify the size to 1 millimeter in this case. Okay, I can go to advanced options. So as you see, we have some advanced options for example, to merge nodes. If we have many parts, we can choose the automatic measure. So as I mentioned before, we have 3 automatic measures for 2D element, let's say for 2D cases. So I can choose between the loop, grid, and the Lunay mesh. So let's choose the loop measure, for example. Actually, we can stay with the Lunay, and let's check the quad elements. Let's click OK, and let's click on the preview button. and let's create the mesh. So this is our mesh. So if I go to this mesh branch into my model worktree, I can right click on this group and display, for example, nodes, and let's hide them. Oh, excuse me, let's hide nodes only. Okay, and let's create the property for 2D case and material. So material has been loaded automatically, similar to the previous model, and has got exactly the same values as the previous one. So I'm displaying that just to remind this step. Okay, so I'm clicking on OK, and let's define the 2D property. So similar to the previous model, I'm going to define the property, but this time for the two-dimensional objects, let's say the entity which is needed is the thickness. So we are not talking anymore about the moments of inertia, because this is the property of the 2D objects that we need only thickness at this moment. So let's keep the 1 millimeter. We can also display the thickness. So now I'm hiding and displaying the thickness for the 2D blade element. Okay. Okay, so done. Now, because let's go to the static and heat analysis step, and let's assign the constraints, and we will use the feature of the symmetrical condition. So now I'm clicking normal to set up the view, and I'm clicking on the constraint. So from this dialog box, I'm clicking on advanced tab, and let's take a look on the working global plane, what the working let's say coordinate system and global coordinate system. So we have some predefined buttons here. So if we take a look on this edge, we see that the edge is parallel to the zeta and y plane. So to assure the symmetry, let's click on this button, and this will assure this condition. So this is the first thing, and now we have to select the objects, and using the selection tool toolbar, I will check the edge. So now I'm selecting nodes on the edge. So as you see, 26 nodes has been selected. So let's click on apply. Let's repeat the same procedure. So I'm using the selection toolbar once again. I'm clicking on the edge. I'm selecting the edge, and this time my symmetry plane is X zeta. So I'm clicking on this button, and I'm clicking on OK. So the model has been constrained, and at this moment the response of the model will be similar, actually very similar, or we can say even the same as for the full geometrical model. So we have the constraints, and let's assign the loading, and this time this will be the pressure, and the pressure will be defined on the element edges, but I will use the geometry edge to find these 2D element edges. So I'm selecting this. So 10 element edges has been selected, and let's enter the value for the pressure. This will be 25, and let's check the direction using the preview button. Okay, so right now the direction is opposite. I want to create pressure in the let's say opposite direction, because this plate is supposed to be subject into the tension. So let's add the minus, and let's click on OK. Okay, fine. And at this moment I'm clicking on analysis and results, and I will create the linear static case. So the static case has been created. Let's go and check what has been added automatically. So everything has been added automatically by NFX, even with the title. So now I'm clicking OK, and let's calculate the model. Let's save, and let's display the results. So as you see, now I'm displaying the total translation vector, and I will insert other results. So let's select all. So if we want to display the translation along y-axis, I can click on the T2 translation, and we can take a look on the animation. Another interesting feature for the post-processing is the symmetry, is the mirror plane feature. So if I click on that, I can specify the mirror plane. So this is one plane, and let's enter the 0, and let's specify the second plane for the symmetry, and let's enter the 0, and as you see on the screen, we can display the results of full model, even with even in this situation when the model has been reduced to the quarter. Okay, let's display, for example, von Mises stress, and we can use some probing tool to check the value directly on the node. Okay, so that's all about the 2D example, and now let me show you the last example, which refers to the 3D case, and we will create some simple pillow box, and this time the geometry will be created manually, similar to the previous examples, because we are working in the analyst mode, and I want to show you that we can do a lot even using these tools which are implemented inside midasNFX. So this time the model type will be 3D, Newton millimeter. Let's click on OK. Let's click on the define grid, and let's change the density for the grid, and at this moment let's enter the value of 10 millimeters. Okay, and let's sketch the geometry. So I will create step by step the geometry from the 2D, and I will extrude created entities into 3D later. Okay, so let's start. So location is, let's start from the rectangle actually. So I'm clicking on this comment, and let's specify the location. So in this case, my coordinates looks like following: -0, let's say, and -100 for the first corner. Apply, and relative values 200 and 200 for the opposite corner. So I'm checking the option make face, and I'm clicking on apply. So the plate has been created, and right now I will create two circles, and first coordinates are 150 and 40, and radius is 20, and let's create another circle, 150 minus 40, with the same radius. Okay. Let's cut this plate, and to do that I will use the tools from the divide box. So at this moment I would like to cut my surface, and let's select these two circles, and direction, let's this will be direction of the shortest path line, so it's not necessary to specify, let's say, the global direction, and NFX will find the closest path line and will separate the faces. So I'm clicking on OK, and as you see, this plate has been splitted. Okay, so I have this plate. Now I'm going to extrude this into 3D. So I just checked my object. Let's select the direction. I can use the global datum axis, and let's specify the value for the length. Let's check the result. So everything looks fine. So I'm clicking on OK, and the 3D geometry has been created. So if I go to the geometry branch, you will see that everything what I made since now has been grouped. So if I uncheck this extrude, I have all geometry data, and each of these geometry data is independent, so which is, I think, advantage if we want to keep the information about the even history, or if this maybe some information will be needed for the future purposes. Okay, so now we have this base, let's say. The second step is to let's say changing the work plane. So I will use this command, move the work plane, and I will move this work plane using the face. So I want to create work plane on that face with the reference to the origin. So this time let's specify 0, 150. Let's click on preview, and let's click on OK. Now I can click on the normal view, on the front view, and let's hide the extrusion, and let's create another shape. So I will use the line. So I will start from this point, 0, 100. After that, from this point, 100. So this is the second line, 60. Okay, so I will hide this datum axis, and next I will create the circle with the radius of 14. So 1, 2, 3, 4. Okay, and I will finish this with that line. Okay, and let's create the arc from that point and this point. So let's hide the grid at this moment, and once again let's use the intersect tool to split this circle. So I'm clicking on OK. Let's delete this part, and the shape has been created. Let's display the extruded geometry once again, and let's go to the protrude command, and let's give to this shape the third dimension. So I'm selecting all of these edges. Let's display this datum axis. Let's check this direction, and this is global Y datum axis has been selected. For the length, let's enter the 50, and let's click on the preview to check. So let's reverse the direction, and if you want to fuse the geometry, we can check this box, but at this moment let's make a solid only. Okay, so the second part has been created, and right now I will create the rib. So I will use the polyline, and let's select the 3D polyline. Let's check the snap options. So let's uncheck the grid snap, pink. Let's keep the point snap. Let's uncheck the middle snap, but let's keep the perpendicular snap, and let's create the polyline. So now I'm creating the rib. So as you see, the geometry for the rib has been created. And similar to the previous steps, let's create the rib. So I'm clicking on the edge, selecting this. I'm selecting all of these three edges. Value is length is equals to 10. Let's check. Okay, I forgot about the direction, so this time this will be x-axis, opposite direction, so please reverse the direction and click on OK. So the rib has been created. And the last thing related to the geometry, let's create some cut in that place. So I will move my work plane again. So I'm clicking on that on this command. Let's move to that face and let's click on preview. It seems that the origin is in the good position, so I'm clicking on OK. I'm going to create the circle and my radius value will be 50 and OK. So using the same option like extrude, I will make some cut in the geometry. So once again, edge, I'm selecting this edge. We have to select the direction, and this time it will be Y again. The value for the cut will be 10, and let's check this option, make solid extend geometry cut, and we have to select the base shape because we have to define which shape will be subjected to this cutting operation. I'm clicking on the preview, so it seems that everything looks fine, and let's click on OK. Let's hide all of these curves, and let's hide the datum axis and working plane, and it seems that the model has been created. So at this moment I'm going to fuse all of these shapes. So I will use the Boolean operation fuse. I'm selecting all of these three shapes. Please merge the faces and let's click on OK. So now, as you see, I created one part, and let's change the name to pillow box. Okay, and right now let's create quickly the 3D mesh, and we will use the 3D mesher. So I'm clicking on this option. Let's click on this, let's select this geometry, let's specify the value for the mesh. Let's create the property. So for the 3D property there is no need to specify any additional value, so only thing we need is to have the material data. So I'm clicking OK. Let's change the name to pillow box mesh, and let's click on OK. So the mesh has been created, and at this moment let's apply some loading. So I'm going to apply the pressure on face. I'm selecting this face, for example, and the value will be like 1000 megapascals, so we can check the orientation for the pressure, and it looks okay. Additional step is to assign the constraint, and let's fix the bottom face. So at this moment, as you see, I'm using the geometry instead of mesh. So I'm using the geometrical entities to define the boundary conditions. So I'm clicking on apply, and I will fix this face, and let's provide the symmetrical boundary conditions for these two faces. So I'm selecting the object type for face. My plane is parallel to y and zeta, so I'm clicking on y and zeta, and I'm selecting these two faces, and done. So let's create the linear static analysis, the same, and let's solve the model. Let's wait a few seconds. Okay, done. So our model size is 12,000 elements, and the calculation is 4 seconds, so you see the midasNFX is really fast. So let's display the results for the 3D objects. Let's display the animation with the auto scale factor, so we can change the scale from real scale to 0 to 5 and 2 from this let's say menu, but if it's needed we can change the deformation scale from this panel, and we can enter the value what we need, for example 5, and as you see the model looks a little bit different. Now I would like to show you the graph on the curve. So this is the graphing directly on the model. So for example, let's click on this point and this point, and direction is plus zeta. Let's display the graph, and let's click on OK. So you see we have a graph directly on this edge. So it was okay. It was okay. It was everything about the tutorials and examples for today. So if you have some questions, now there's a time to ask, and I hope my colleagues already answered you a few questions. I received some questions in, let's say, many languages. One of the questions is in Polish, so I will, let's say, answer about that. I will translate this into English, because one of the participants asked what's the difference between the modeling when we are using the force and displacement, and the question is, should I block the movement on the force direction when I want to use a force, and or should I leave this, for example, if I want to use the displacement? Yes. So if we want to use the force, usually the direction for the expecting deformation of or let's say acting force direction should be free. Let's say displacement is itself a constraint. It's actually the same definition, because constraint is displacement with the value of 0. So from the, let's say, numerical point of view is actually the same. So there is no need to constrain the displacement in NFX. Okay, I think so. If you have some more questions, I would like to ask you to write to us these questions via emails. So I would like to invite you as well to visit our web page, which is midasNFX.com, or visit our channel midasNFX and /SciPNR. This is a channel of our marketing manager. So you will find a lot of interesting tutorials and interesting materials, and I hope you are satisfied about this webinar. And so that's all for today. So thank you very much. and see you on Tuesday, where we will handle material non-linearity examples in terms of metal forming. So I would like to invite you for that webinar, and I will show you two examples. Let's say one big example for the metal forming, and second one it will be a little bit more difficult, but in terms of the type of analysis. So this webinar will be focused on the nonlinear implicit quasi-static analysis and explicit analysis for the metal, for the deformation in metals or handling nonlinearities in metals. So thank you very much, and see you on next Tuesday. Goodbye.
The organizer has ended this session.